Physical Chemistry, Part 1, Thermodynamics, Chapter 2, Heat, Work, Internal Energy, Enthalpy, and the First Law of Thermodynamics. Section 2.1, the Internal Energy and the First Law of Thermodynamics. What's the first law? It's simple. Energy cannot be created or destroyed. Energy can be transferred from one form to another, from one body to another body. But again, the energy cannot be created or destroyed. The total energy of the universe is constant. The internal energy of an isolated system is constant. Remember, the definition of the isolated system is that there's no energy exchange or matter exchange between an isolated system and its surroundings. Now let's define internal energy. The internal energy is the sum of the potential energy and kinetic energy within the system. So for example, water in a fast-moving airplane has exactly the same internal energy as the water on the ground, despite the fact that the water in the plane is moving and also the water in the plane has a higher altitude. Because of the first law, we know the change of the internal energy of the universe is always zero. Therefore, the change of the internal energy of the system plus the change of the internal energy of the surroundings is zero. And similarly, the change of the internal energy of an isolated system is zero. If a system is not isolated, it can be an open system or a closed system. The internal energy of such a system may change due to either heat or work. We have a nice equation here. The change of the internal energy of a system is equal to Q of the system plus W of the system. Q is the amount of heat that flows into the system. W is the amount of work done to the system. What if heat is flowing out of the system? Then Q is negative. What if work is done by the system to its surroundings? Then work, W, is negative. For convenience, if we're talking about the change of U, Q, and W for the system, we can drop the subscript. So delta U is equal to Q plus W. Here, delta U, Q, and W are referring to the system. Q surroundings is always equal to negative Q. W surroundings is always equal to negative W. It's simple. If, for example, 1 joule of heat flows into the system, where does it come from? The surroundings. What if 1 joule of work is done to the system? The surroundings does that 1 joule of work to the system. The differential form of delta U equals Q plus W is du plus dq plus dw. So pay attention to this strike here and strike here. The reason is dq and dw are inexact differentials. So we put a bar across this d. What are inexact differentials? They cannot be integrated, only given the lower and upper limit for the integral. We have to know the entire integration path to be able to integrate dq and dw. Let me give you one example. Y dx is an inexact differential. We cannot integrate this y dx given the lower and upper limits of x and y. Let's say the lower limits of x and y are 1 and 1. The upper limits of x and y are 2 and 2. How do you integrate y dx? There's no way to integrate y dx. We have to know how y changes with x before we can integrate this y dx. However, dxy, the differential of the product of x and y, is an exact differential. So we can integrate this dxy given the lower and upper limits. So the indefinite integral of this is x times y, or xy. And then we can integrate this from 1, 1 to 2, 2. What's the integral value? It's simply 2 times 2 minus 1 times 1. The result is 3. And a reminder, this dxy is the sum of y dx plus x dy. It's just the product rule in multivariable calculus. All right, so again, y dx is inexact, x dy is also inexact differential, but the sum of y dx and x dy is an exact differential. In this chapter, we will study adiabatic, that means Q is 0. Isothermal, that means temperature change is 0. Isochloric, that means volume change is 0. And isobaric, that means the pressure change is 0. We will study these 4 different types of processes.